Thank you very much for allowing me to join you. I am in California, where it is 1 o'clock in the morning. So if you will permit me, I will drink some coffee during our talk. Uh, this is a really interesting meeting between power quality experts and experts in electric vehicle chargers. So I will try to address some of this talk to each of the two different groups. First, electric vehicle chargers are often the biggest single load in a residence, in a house. This picture at the top is my home laboratory. The electric vehicle charger, which you can see there, is in fact almost an order of magnitude larger load than any other load in my entire house compound. Um, and even so, I have limited it to just 4 kilowatts, but I don't have any other electric load that is more than about 300 kilowatts. So two comments about that. One is that the infrastructure for bringing electric power to the charger in a residence can be quite an issue. This particular residence, this particular building is 110 years old, and I had to do rewiring for it. But also, many residences, including this one, have photovoltaic inverters, and there can be difficult interactions between the control loops of the inverters and the control loops inside the chargers. There was a brief mention of superharmonics in the introduction, which I'm glad to see. We'll talk more about that in a moment. But the other issue to think about is that with these very large residential loads, they can wind up being synchronized with each other. And usually we think about the synchronization of the charging algorithms, but they're also synchronized by power quality disturbances. When there is a brief interruption, for example, all of the chargers start up again at the same time, and that can create power quality problems as well. The other kind of charger, community chargers, are very, very large loads for the grid. And I thought the best way to explain that is with this little map of California. There are two large cities in California, Los Angeles in the south and San Francisco in the middle, the two circles on the map. And if you've ever traveled to Los Angeles, which is where I grew up, you know that you must have a car to get around Los Angeles. You can't move in Los Angeles without a car. So if you want to travel from San Francisco to Los Angeles, yes, you can fly, but when you get there, you must have a car. It's often easier simply to drive, to take a day and leave San Francisco in the morning and arrive in Los Angeles in the late afternoon. If you have an electric car, most electric vehicles can travel 400 kilometers or so, and halfway down California along the main high-speed highway between San Francisco and Los Angeles is a very good restaurant. And the restaurant is called Harris Ranch. If you ever get a chance, it's worth going. And they are famous for their beef. There's nothing else there except for many, many, many cows. But there is this one restaurant that's halfway between San Francisco and Los Angeles. And so everyone who drives an electric vehicle wants to charge at Harris Ranch during lunch. And so Harris Ranch has installed 50 high-speed chargers. Each of the chargers draws about 250 kilowatts, so they can charge a vehicle very quickly during lunch and then move another vehicle in. So we have about a 10 megawatt load at Harris Ranch, but it only occurs very briefly during the middle of the day. However, The utility infrastructure, the electric company infrastructure is not good at Harris Ranch because there's nothing there but cows. So suddenly we add a very large load, very intermittent, and that causes problems with the power quality for a lot of Central California. So sometimes with these new chargers, the best use location, like Harris Ranch, can be the worst power quality location because it's so far away from the rest of the infrastructure. Power quality is important to electric vehicle chargers too, but just to make sure we all understand, quality usually is measured for most things by how far they are from perfection. If you are talking about diamonds, it's how many flaws are there in a diamond. If you were talking about the quality of a person, probably it's their honesty and the perfection of their personality and how far from that they are. But power quality instead is intermittent. It doesn't occur, it doesn't stay constant like the quality of a diamond. And it's not the distance from perfection. Power quality is compatibility. And there are three questions. First of all, is the power good enough to operate the load? Can we operate the electric vehicle charger with this piece of power that's available on the outside of my test lab? The second question is the load strong enough to operate with the power that's available? And finally, is the load careful about not disturbing the electric power that it shares with everything else on that particular part of the grid? All three of those characteristics together is what sets power quality. It's the question, is the grid compatible with the load, and is the load compatible with the grid? You notice that that means that power quality changes when we introduce new loads, because the new loads have new characteristics. In fact, power quality was not a problem up until about the 1970s, when mini computers were introduced, because until then, all the loads were lights, heaters, and motors, and they didn't care about voltage sags or harmonics or anything else. But when we introduced mini computers and tried to power them from regular main sockets, they didn't work very well. And that's when the whole concept of power quality developed. Now, you might think that electric vehicle chargers are not a new load because they've been around. Well, I built my first electric car in the early 1970s. So electric vehicle chargers have been around for 40 or 50 years at least. But in the time scale of electric grids, that's new. And electric grids generally are designed to operate for 100 years. Equipment that's installed on electric grids is often rated for a lifespan of 70 or 80 years. So when you start bringing in large amounts of electric vehicle chargers, that's very new. Standards are very useful for compatibility, but they are not carved in stone. I have spent the last 30 years writing standards mostly for power quality. And I can tell you that standards begin with blank pieces of paper and groups of engineers who are trying to improve the compatibility. We do a very careful job of writing the standards. It takes years to write them. And the people who write them truly are experts. In that picture, I counted, and I believe there are almost 700 years of experience. And each of those people writing the standard is the top expert on the subject in their country. And their countries include South Africa, Japan, China, I can see Belgium and Austria and England and France and New Zealand and Australia looking around that table, the United States. So you have a group of great experts trying to write a standard. Keep in mind that standards are not written when there is a single correct answer. If there is a correct answer, you don't need a standard. You don't need a standard to say that 2 plus 3 equals 5. 2 plus 3 does equal 5. You only need standards when there are many different correct answers. And it's important that we agree on one answer. Then you need a standard. So, for example, what should the connection between an electric vehicle charger and an electric vehicle look like? How many pins? How much current? Well, there's lots of possibilities. How far apart should the pins be? But it's very nice if we can all agree on just one. And that's why standards are so useful. Given that power quality is compatibility between loads and the grid, it's important to communicate that compatibility with standards. But unfortunately, power quality standards for electric vehicle chargers are not yet available. They're being worked on, but for the moment, we must rely on standards that are written generally for power quality or for power quality for residential use and power quality for industrial use. If you're not familiar with power quality standards, I suggest that you begin with IEC 61430, which is the power quality measurement standard, because it lists all the different possible disturbances on the grid and contains measurement methods, which is really how these disturbances are defined. IEC 61411 and 434 are standards for voltage dip immunity, and voltage dips are the most common disturbance. If you're immune to voltage dips, you're pretty much immune to most disturbances, but there are other kinds of things you have to consider. To those of you in the charger engineering segment of our meeting, I would like to pose a quick question. If you have designed a charger that will work anywhere in the world, it probably will work anywhere from 100 volts in Japan to 240 volts or 260 volts in Australia. So if you are operating that charger at 230 volts, can you be reasonably sure that the charger will work correctly if there is a brief reduction in the voltage to 50%, to 120 volts, and then it goes back to 230 volts? Most engineers who are not familiar with power quality would say, of course, it's rated to operate at 240 volts. If you lower the voltage to 115, no problem, and bring it back up half a second later, no problem. The charger will work fine. But no, that's not generally true. And that's why standards like 61411 and 61434 are so useful. If you look at the graph, the simulation in the center there, the red line is the voltage waveform, and the orange line below it is the current waveform. In this case, just a bridge rectifier and a bulk capacitor. You can see the voltage sag in the voltage to about 50%. The key thing to notice is that there is a big inrush current at point B. The current at B is perhaps 2 or 3 times higher than the current at A. And that inrush current is obviously because we're recharging the bulk condenser. Forgive me for switching between American English and British English. Capacitor in American English, condenser in British English, it's all the same. Of course, we have inrush current limiting on our designs for chargers, but generally that inrush current limiting is in place only when power is first applied, and then we bypass it. So if there is a voltage dip, and the inrush current limiting has been bypassed, at the end of the dip, there will be a big inrush current. And when that happens, you can create more voltage sags for everyone else, or you can cause circuit breakers to operate, or you can cause fuses to blow and rectifiers to blow. That's why these standards, for example, say you must have at least 400% of the rated current for the device that you're testing available in your test source for doing voltage sag immunity testing. And that's why generally you don't use electronic sources for voltage sag immunity testing, but instead use transformer tap switching sources like the one at the bottom right, excuse me. So look at these standards for learning more about power quality immunity testing. I thought it might be useful if I briefly discussed not so much a project that I'm working on right now for the United States Department of Energy, but the mistakes that I'm making in that project or have made. This is an interesting project for designing a new piece of power electronics that operates just at 40 kilohertz with silicon carbide FETs. There's nothing particularly special. It's only a kilowatt load, and then there's some very, very special instrumentation that goes with it to look at the interaction between control loops on the grid. But when I sat down to design the power electronics segment of this device, the first mistake I made is in my simulation. I said, well, I'll just put in a 230 volt, 50 hertz source right here. Boom. And there I put it into the simulation. I didn't put in any source impedance. And that, of course, gave me a very unrealistic power quality set of measurements. So I fixed that. And then the simulation worked fine. But I made the simulation, and this is embarrassing. I'm a power quality specialist, but I made the simulation assuming that the 230 volts was constant. And of course, it's not. So I put in variations both in the magnitude of the 230 volts and the frequency and the rate of change of magnitude, and got everything working fine. But my third mistake was paying attention to how well the circuit that I was making works. I was looking at my circuit, not at how my circuit was affecting the grid. And so when I fixed that, it became clear that just thinking about voltage variation and rate of change of voltage variation, it was not sufficient. I needed to include harmonics and harmonic filters. When I actually built the circuit, and of course I have photovoltaic inverters here, and just, you build it, it's just a 1 kilowatt load. I'll just plug it in and see what happens. It began to interact with the control loops on the photovoltaic inverters. And that's because I hadn't tuned my own PID control loops to ensure that they were stable when a different control loop was raising and lowering the voltage. Just an aside, when I plugged in this 40 kilohertz switching load, several of my ground fault interrupters, I can't remember what they're called in Europe, but the protection devices that prevent earth currents, several of them in my house, which is 100 meters away, tripped. And that was because of the superharmonics being generated by the power electronics load that I had just plugged in and I hadn't filtered properly. The last mistake number 6, I'm sure there are other mistakes I've made, but I don't know what they are. We'll find them and fix them. But I just thought it might be interesting to let Other power engineers who are working on electric vehicle chargers know that even experts on power quality sometimes struggle with their designs. Chargers can solve a problem for the grid, but can also create problems for the grid. You may be aware that much of the grid relies on massive rotating machinery for its stability, particularly in the generators. As a rule of thumb, in a large grid, say the Western European grid or the Western North American grid, there's almost no storage. Over short periods of time, almost zero storage. Short periods of time meaning a second or so. For a fraction of a cycle, there's lots of storage in power factor correction capacitors, but that by their nature is designed to last a fraction of a cycle. Over the course of hours, there's lots of energy storage, sometimes in water height storage and things like that. But over the course of a second or so, there's almost no storage. That means that looking at timescales of half a second to 2 or 3 seconds, 10 seconds, the energy being inserted into the grid by all of the generators combined must exactly match the energy being taken out of the grid by all of the loads and the grid losses combined, because there's nowhere to store the energy if there's any excess energy. So this should raise an interesting question in your mind. When you go into your kitchen in the morning and turn on a heater, an electric heater, to make hot water for your coffee, let's say 200 kilowatts, where does that energy come from? You have suddenly added a 200 kilowatt load to the grid, and there's a perfect match between the generators and the loads. Is someone watching you saying, look, he just turned on 200 kilowatts. We should crank up the generators by 200 kilowatts. No, that doesn't happen. What actually happens is when you turn on your 200 kilowatt load in, let's say, Paris, all of the generators in Western Europe slow down very slightly, just enough so that they release an extra 200 kilowatts altogether of energy, of power, by slowing down, and that energy comes from their reduction in rotational inertia. That's where the energy comes from. Now, we are gradually removing those rotating generators from the large grids. We've removed the coal-fired generators. We're talking about removing gas-fired generators. Some countries are removing the nuclear generators, and they're being replaced with inverters. There are solar inverters. They're being replaced with inverters being operated from large grid-scale batteries, inverters operated from wind turbines. Inverters work very well, but they don't have any rotational mass, so they don't store and release energy. The short-term grid stability is still being provided by all those beautiful rotating generators in the nuclear plants all over France. As we shut down rotating generators and replace them with inverters, we are going to need to add energy storage that can be released over the course of a fraction of a second to a few seconds. Electric vehicles are storage points for energy. And an electric vehicle that is charging is already connected at one end to its battery and at the other end to its grid. So it's very tempting to think about using electric vehicle chargers as inverters. When the grid needs support, they can pull energy from the vehicle and push energy onto the grid. And there have been large experiments in that direction in Japan. I was measuring the power quality in some of those experiments. And there are experiments going on now in China and in various locations around the world. And it works very well, except for the control loops and how they interact. Of course, every inverter has at least two nested control loops, one that is trying to match the sine wave or close to sine wave of the voltage on the local grid, match its magnitude, and a second one outside that that is trying to control the amount of power flow that is going through the inverter and is being pushed onto the grid. Two nested control loops can be made quite stable if there aren't any other control loops sharing the grid. But when there are many different control loops from different manufacturers, instabilities can result. And aside, this turns out to be a societal issue, a cultural issue as well. In Japan, there is a very good tradition of shared resources from individual owners. There is a sense of responsibility that each individual has towards the rest of the society. That's not so true in America and Australia. And perhaps the best example of that is in this time of COVID-19. The simplest thing we can do is wear masks. It doesn't cost anything, it's easy to do, but there's a lot of resistance in some parts of America to wearing masks because we are independent. We don't want to take instructions from everyone else. So there are cultural issues with using electric vehicles as energy storage sources that the grid can call on. Just an aside there. But of course, when the electric vehicle is being used as an energy storage source, it is a source of power quality disturbances as well. Electric vehicle charges are fairly easy to design to tolerate power quality disturbances, and they're fairly easy to design to not emit power quality disturbances. But doing both of those increases their cost. To tolerate power quality disturbances, you have to store energy somehow, usually in bulk capacitors. And to reduce high frequency emissions, particularly infraharmonics, you have to add inductors and capacitors, but mostly inductors. And as you know, bulk capacitors are large and inductors are heavy. And both of them add cost, both initially and in lifetime. Capacitors tend to be, other than fans, capacitors tend to be the shortest lifespan in any component in a design. And in the cost of shipping. When you add weight, it gets more expensive to ship. And at the same time, you must increase your design margins. If you think that you're designing for 100 volts to 240 volts, that will cover the globe for single phase. And perhaps you say plus or minus 10%, so you design for 90 volts to 264 volts. Well, you're going to need to go below 90 volts and above 264 volts. And that, of course, going below 90 volts increases the current ratings of your semiconductor devices, and going above 264 volts increases the voltage rating requirements, and suddenly everything gets more expensive. I will mention Georges Simard, my friend at Hydro-Quebec, retired from Hydro-Quebec in Canada, who also is an expert in judo, which is the fighting technique where instead of going directly against your opponent, you allow your opponent to rush at you and then step to one side and push your opponent as he goes by. And Georges suggests we do the same thing with power quality, that we don't try to design electric vehicle chargers to tolerate and operate properly when there are power quality disturbances. Instead, we allow the electric vehicles to stop operating, to fail. We say that's okay. You can fail when there is a voltage dip, but you must turn yourself back on gently and easily and begin operating again properly after the voltage dip. This has been the approach in the semiconductor manufacturing industry, and it has worked very well. So it may be possible to use firmware in your vehicle chargers to become immune or more immune to electric voltage quality disturbances. As you add cost to your design, your management will say, why do we need this additional cost? If there are standards that say you must tolerate these disturbances and you must be tested to tolerate these disturbances, like the ones ELAD is working on, then that is a simple answer. But those standards aren't here yet. If there are certifications you must meet from governments, the S mark in Japan, the CCC mark in China, the South African power quality immunity standards, that may be a justification. If your customers are knowledgeable enough, like the semiconductor industry, that your customers themselves have a standard saying you must tolerate this voltage sag, this voltage dip, or we will not pay you. That is a good reason to increase your power quality immunity. And that has been financially very successful in the semiconductor industry. The suppliers of the equipment have said, well, then we must raise our prices by 8%. And the payback for the customers of the equipment has been far, far, far more than the increased cost of the equipment. You might be able to say to your management, this will increase our reliability, and that will directly reduce our service costs because customers will not call us because they've had a power quality disturbance. Instead, our equipment will operate properly. Or you could justify it based on your reputation. But in my experience with devices like electric vehicle chargers, this is the biggest challenge in making them immune to power quality disturbances. It's justifying the additional cost to management and to customers. From a technical standpoint, power quality problems are intermittent. And so if you think you have an intermittent problem, that is the most difficult technical problem to solve. And once you've solved an intermittent problem, you don't know that you've solved it. Because if it happens once a year or once every 3 years, and you have a field population of 30,000 devices, and it seems to affect 100 of them, if you put a fix in, you won't find out for years whether your fix actually solved the problem, if you were correct about your speculation. So for this reason, I strongly recommend, if you can, and it's almost free, design in a little bit of power quality recording inside your EV charger design, so that if you do get intermittent failures, at least you have some data saying this is what the power looked like when our charger failed. There are different problems in different countries. In Japan, for example, the source impedance is very low, perhaps 5 times lower than it is in Germany. As a result, voltage dips tend to be much smaller in Japan, but fault currents are much larger. In South Africa, the impedances tend to be higher and the voltage dips tend to be more common, and especially during the sugarcane harvest season. Um, in North America, there is a significant difference between the power quality in, say, Florida, where there are many lightning storms, and, say, in California, where the problems are more associated with other sources like photovoltaic inverters. And again, the control loop interactions with inverters and EV chargers is something to be aware of. There is a new challenge that is going to be addressed at this conference. And as someone who has been working on power quality for almost 50 years, I'm really happy to see you working on this. Superharmonics are emissions from electric vehicle chargers in the 2 kilohertz to 150 kilohertz range. The reason they're a problem is that there are standards that set limits on emissions up to about 2 kilohertz, up to about the 40th harmonic of 50 hertz. Those are the harmonic standards. There are standards that set limits on 150 kilohertz up to a few gigahertz. Those are the EMC, electromagnetic compatibility standards. But in the frequency range between 2 kilohertz and 150 kilohertz, there haven't been many standards, and that's because there haven't been problems. Until these large switching loads, like EV inverters, that tend to switch at 40 kilohertz or 60 kilohertz, began putting these large emissions onto the grid. It isn't a big problem yet, but it's very good that we're addressing this problem before it becomes a huge problem. And that's going to be one of the topics of this conference. I'm very glad to see these two different communities coming together, the power quality community and the electric vehicle charger community. This is going to be a wonderful conference. You have some great speakers. My friend and colleague of 30 years, Professor Math Bolan, will be talking about the research going on superharmonics. My friend, Professor Jan Meyer, will also be talking about the superharmonics research that his group is doing. It's a wonderful collection of speakers that ELAD has assembled. My only regret is that we cannot all be there together in person. We cannot have a beer together. We cannot drink coffee and trade ideas together. But I hope that a year from now, there will be a good vaccine and we will all be able to sit down together. And instead of me being in California at 1:30 in the morning, we will all be together in the same time zone and be able to share ideas and share our time together. I wish you a good conference and thank you very much. Perhaps there are questions.
Well, first of all, Alex, thank you for your very interesting presentation. And I'm also looking forward to seeing you in real life. Maybe next year we can host another event, indeed, maybe really at a location. We can actually meet each other. Would be nice. First, I have some questions. I had a question myself. I was wondering, because you were saying maybe it would be wise to start recording power quality events in the electric vehicles. I was wondering, what kind of measurements would you like to do in these vehicles? Would it be the voltages, the currents?
Yes, perhaps I misspoke. I did not suggest recording. I did not mean to suggest recording in the vehicles. I suggest recording in the chargers.
The chargers,
And,
okay. Yeah.
I would like the chargers to record information about the AC input voltage to the charger. And the reason is that that is part of the environment for the charger. You probably are already recording the temperature in your charger. So if it goes over temperature, your service people can know that. But if you look at the IEC standard on power quality measurement methods, some of the very common disturbances, voltage dips, for example, are easy to record. And if the charger would simply save the timestamp and the depth and the duration of the voltage disturbance, that would be useful for your own service of that charger. If the charger fails, but you see when it failed, there was a big voltage dip, you can say, well, not our charger. The problem was with your electric power. But it also will give you, as the designer, a statistical database about the electric power quality where your chargers are installed. The electric company will have useful information about power quality on the grid. But the general rule of thumb, the general sense is that about 80% of power quality disturbances come from inside the building. So inside the home, inside the factory, all those, there are many different ways there can be disturbances. So your vehicle charger is not getting the power quality from the grid. It is getting the power quality right where it is installed. And you should be recording that. Perhaps as simple as the RMS voltage recorded every 200 milliseconds and discarded unless it goes outside some limits.
Okay, excellent. We have a related question from James Meyer. Like you just said, James Meyer, not John Meyer.
Oh, okay.
Almost the same name indeed. But it's also related to what you just said, that distortion probably comes from the building or the household and not from the grid itself. Because he says, I've been told that superharmonics mute away in an electrical grid. And is that true?
Well, I think both Jan Meyer and Matt Bolden will address this in more detail. But the short answer is that an electric grid is not capable of moving, well, back up. Electric power is simply a way of moving energy from one location to a different location. That's all it is. It's not a source of power. It is a method of movement of power. Grids in general are very good at moving power between about 30 hertz and about a few hundred hertz. But for very short distances, you can move power at up to about 100 kilohertz, 150 kilohertz. And by short distances, I mean tens of meters, perhaps hundreds of meters. And the easiest way to see this is how lightning strikes propagate through a grid. A lightning strike is a very, very brief high current applied to the grid. Brief on the order of a microsecond or 2 or 3, followed by a 10, 20 microsecond aftershock. But throughout the grid, you will generally see that as a damped ringing wave at about 100 kilohertz. And that's because the grid in general has a resonance at about 100 kilohertz. And if you try and move things through higher than 100 kilohertz, it doesn't transmit. But between about 2 kilohertz and 100 kilohertz, the grid is a lossy transmitter of energy. But over short distances, you can get a lot of energy transfer. And one of the big problems, of course, is that all of us have electronic devices throughout our factories and houses. Those electronic devices have capacitors connected from line to earth to minimize high frequency noise emissions. Those capacitors are sized with the assumption that we're dealing with 50 hertz. If you suddenly apply 40 kilohertz or 50 kilohertz, the impedance of those capacitors go down by 3 orders of magnitude, and you suddenly get a lot of earth current and things start tripping. And that's the big problem with superharmonics. There are other problems, revenue meter problems, but the earth current tripping problem is the main one.
Okay, excellent.
A long answer to a short question.
Yeah. Well, in the meantime, we've received a lot of questions actually. I do see one that's also a bit similar because it's also concerning the cables, how important the role of cables is, but well, cables and of course the length of the cables. Like you
And again,
just
we're talking about the cables on the AC side of the inverter, not the charging cables between the inverter and the electric vehicle. I want to make sure that's clear.
Yeah, excellent. I just heard that we have 2 minutes left. Let me see if there's one final question that would be interesting to ask. There are a lot of people saying that the presentation was really nice, by the way.
Oh, thank you.
Let's see. Oh, that's yeah, there's more general question, maybe more also for the panel it will be interesting, but if the EV becomes a power plant, as suggested, vehicle manufacturers might decline guarantees to the battery. How would you suggest to deal with it?
I don't know is the short answer. That is the primary question. Should the owner of the battery or the owner of the vehicle be paid for briefly providing energy? And if so, how much? The other issue is that if the owner expects to be able to use his or her vehicle and the battery has been depleted, has it been discharged because there was a problem on the grid, well, now what? So I don't know the correct answer. I do know that when there are, in some ways, we are already using electric vehicles in California as emergency sources of power in a very simple way. You may know that about a year ago, we had huge fires throughout Northern California, and that shut down much of the electric power grid. The main thing people need to do is charge their cell phones. Well, you can go to any electric vehicle and plug into the 5-volt USB port and use the electric vehicle to charge your cell phone. And some of them, some of us simply drove around saying, does anybody want to charge your cell phone? Here you go. So in a very small way, that's already happening, but compensation and battery life is a big issue. Yes.
Yeah. Okay, excellent. Thank you. This will also be a nice topic to discuss during the panel session later this afternoon. Unfortunately, you won't be able to join, but well, that's of course.
I will be asleep.
You will be asleep indeed. So, well, thank you very much for your presentation. Have a good night's sleep. And well, as said, most of the presentations will be recorded afterwards, so you will also see the presentations from the others.
Thank you
also
very much.
for the other audience, of course. Well, excellent.
Well, I wish
Thanks
you all a good conference. Thank you very much. Goodbye.